Let's talk about inclined planes. What happens when we take an object and place it on a surface that has been raised at an angle, an inclined plane? Turns out that the object has a minimum of three forces acting on it. You're always going to have the object's weight. That's still going to exist. That'll be the object's force as a result of gravity. And that's this guy that's straight down. In addition, the inclined plane itself is going to support the object. Now, if you recall, the normal force is the force that comes from the support of the surface. Really, up until now, we've been primarily dealing with a normal force as anything that's basically, it's straight up. So far, at least it has been. However, that's not really the true definition. If you recall correctly, the normal force is actually always directed perpendicular to the surface. So for an incline, the surface itself is at an angle. So normal force is drawn perpendicular. Turns out that means the normal force is no longer exactly opposed to the force due to gravity. If you look at it on this diagram here, you will see that the force due to gravity is straight down, and the normal force is actually going to be at some angle away from gravity. We're going to come back to that in a minute. Lastly, as long as friction exists, we will always include friction, and it'll always be opposing the direction of motion. So in this example, the motion is down the plane, so the force of friction will be up the plane. Another way of looking at it is it's always parallel to the surface itself. Now, if we go ahead and treat our x, y coordinate system as your typical up and down, that's a terrible coordinate system, let's try that again. As your typical up and down, it's still terrible, isn't it? Up and down and left and right. There you go, much better. You have your y up here and your x over here. Now, if we were to utilize the traditional coordinate system as I've drawn, we would find that the normal force and the force of friction are forces that exist in two dimensions. Now, if you recall, anytime you have two dimensions, you have to separate those vectors into your individual x and y dimensions. This ends up getting pretty tricky for objects that are an incline because we have two different forces in two dimensions. We choose now to do a little math trick. We're actually going to define the xy coordinate system differently. Rather now, we're going to treat the x-axis as that parallel to the incline, and your y-axis as the axis that's perpendicular to the incline. So we're really going to rotate that xy coordinate system that we usually use. So you can see that here, your y is perpendicular to the plane, and your x ends up being parallel to the plane. This allows us to have the normal force exist solely in your y dimension now, and the friction force, or any other forces that are parallel to the plane, can exist in the x-axis. As a result, that allows us to have one and only one force that's in two dimensions, and this ends up being gravity. This will allow our math and our understanding of the overall motion of the object to become much easier. Let's take a look at what that means. Because gravity is now in two dimensions, so again, let's go ahead and draw the xy coordinate system as we're going to treat it. That'll be my y, and that will be my x. Make that x a little more dominant. There we go. Uh, we will see here that again, gravity, the force due to gravity at least, ends up being in a combination of the two dimensions. It's at some angle. What we end up what we end up choosing to now do then is break up that force due to gravity into two dimensions. What I do is I find the component of that weight that is in the y dimension, and I identify the component of the weight that is in the x dimension, as I show right there. We end up calling the y component mgy or fgy, also known as the perpendicular component of weight. We'll do the same for x. We'll call it mgx or fgx, also known as the parallel component of weight. This might not be as easy to see, so what I'm going to try to do is kind of show you this on a larger scale. Before I do that, I want to show about what does that mean. So when an object is flat on a surface, I don't know if you can tell because I'm not going to hit play yet because this is a relatively quick video. You have your block right here resting flat on the surface. In that example, the weight is completely down and it's perpendicular to the surface. So in this example, when there is no incline, the perpendicular component of weight is completely equal to the weight itself. However, as we raise the incline at an angle, you will see that although weight stays straight down, your perpendicular component now becomes smaller because the angle of the incline increases. Not only that, we begin to get a parallel component of weight, which is the version of the weight that's actually causing the object to want to slide down the plane. Now this should kind of make sense. When an object is flat on a surface, it'll never choose to just slide along the surface. So there's no parallel component of weight pulling it. As the angle gets bigger, the object does tend to try to slide, and sometimes it does slide down the surface. However, at shallow angles, it doesn't slide with a very large rate. The rate in which it increases in speed, its acceleration is actually pretty low because that parallel component is much smaller than the actual weight itself. But as the incline's angle gets larger, that parallel component also gets larger, and the acceleration of the object increases. Eventually, we could make it completely perpendicular, and now your parallel component of the weight ends up equaling the weight. The object will be in complete free fall. So how do we go about identifying how much an object's weight is parallel to the incline or is perpendicular to the incline, and what does this mean in terms of our dynamics? So I'm going to draw a free body diagram of an object on an incline, and this is going to be a little bit more exaggerated than what we probably would usually see. So I want you to try to be able to see the forces pretty clearly. So I'm going to make this a pretty large angle theta. I'm not going to put any numbers in, but that's probably almost 45 degrees. Pretty good steep hill. And we're going to talk about this object here that's got simply a mass of m. So for now, we're just going to say mass is equal to m. Later on, I'll plug numbers in so we can get an idea of actually how much the values are quantitatively. And remember, there are always three forces, as long as there's friction at least, for inclined plane problems. Occasionally there will be additional forces, but that'll be very clear, and I'll review that when that happens. So those forces are, again, we've got the weight, mg, straight down. We can also call it F sub g. You've got your normal force, which again is perpendicular to the incline. I'm going to refer to it as Fn. And we've got our friction force. Now this will be an example of an object that is sliding down the plane with constant velocity. Well, what does that mean, constant velocity? What does that mean in terms of our forces? Constant velocity. Well, that should mean, in terms of our forces, if we were to look at them all and add them all up, we'd find out that our net force must be 0 in all dimensions. So in the y dimension, your net force is 0. And in your x dimension, your net force is 0. Now, if the object were, say, accelerating down the plane, then the net force in the y would still be 0, but your net force in the x would be ma. Or if it's just sitting on the incline, perhaps it has yet to begin to move, that static friction force is large enough. That would be an example where it isn't sliding, it's just at rest, but it would actually look identical to the situation here. It would still be in equilibrium, so the net forces in both dimensions would still be 0. However, the only difference now is it wouldn't be moving. But in this example, the object is sliding, and it does have constant velocity. Now, because your net force in the y needs to be 0, and your net force in the x needs to be 0, that means any force that's in the y dimension needs to have at least one other force in the y dimension canceling it out. And the same thing needs to be true for the x dimensions. So now we already said that normal force is in the y, and your frictional force is in the x. So if we look at them independently, let's look at the y dimension first. We need to have another force opposing it to allow for it to stay in equilibrium. That other force ends up being the weight, just not all of the weight. What we need to do is we need to take that weight and find the component vectors of that weight that exist in our x and y dimensions. As I just showed before, but now perhaps it's a little easier to see because this is a larger version. We have the y dimension of the force due to gravity, and we have our x. I'm going to label these appropriately. I'm going to label this one mgx, or mg sub x. This one is mg sub y. This is my 90-degree angle. And this one right here, that is your angle theta. It's the same angle as the incline itself. They're the same. They're equal to each other. Now, if we were to look at each vector individually, oops, they should end up being the same size as their counterpart in the y, and then the same in the x. Now, it looks like I drew my x a little poorly. My force of friction actually should be longer. It should be the same. Yeah. Now, as I just tried to do before, I'm going to slide that vector up. Remember, vectors can slide around. I can't rotate it. I can't make it bigger or smaller. but I can slide it around. So I'm going to slide it right here just so it's a little easier to see how it's that x component of gravity that's responsible for equalizing the frictional force. And it's the y component of gravity that the normal force is equalizing. That's why the object doesn't fall through the incline or whatever. So how do we find mgx and mgy? Well, let me go ahead and undo this. I'm going to move mgx back where it was. Now perhaps you can see that this here is a right triangle. And so we can use SOHCAHTOA to help ourselves find mgy and mgx. So I'm going to take a look at this angle theta here. And I want to say, well, what is mgy going to equal in terms of mg? Well, I see here that mg is my hypotenuse. It's the one that's opposite of the 90-degree angle. And I say that mgy is my leg that's adjacent to my angle theta. Now, if you remember SOHCAHTOA, I'll remember that I need to use cosine because cosine is adjacent over hypotenuse. So I'll go ahead and do it the long way. I won't be writing it out this way every time, but I will right now. Cosine of your angle theta is equal to your adjacent leg, mgy, divided by your hypotenuse, mg. Well, let's say we know the mass of the block. Maybe we'll know the angle of the incline. Our goal then is to find the y component of gravity. So I want to rewrite this for mgy. And this is how I will lead off writing it from here on out. Your y component of gravity, or the perpendicular component of gravity, is equal to mg times cosine of angle theta. We can do the same thing for my x component of gravity. Once again, we're going to look at trig. We're going to see that we have the hypotenuse, mg, and mgx is opposite of my angle theta. So I'm going to go ahead and use sine. I'll say that the sine of my angle theta is equal to mgx, my opposite, over mg, the hypotenuse. Once again, what I really care about is mgx. So I'm going to rearrange that to show that mgx is equal to mg times the sine of my angle theta. And again, that's how I will be writing it from here on out. Let's go ahead and actually look at some examples here. Try to make sense of this a little bit more. Here's a typical Regents type of question. We have a cart rolling down an inclined plane at constant speed, shown in the diagram below. We want to know which letter represents the normal force, the weight, and the friction force. Well, again, as we recall, the normal force is always the force that comes from the surface that's perpendicular to the surface. The only force that's coming from the surface that's perpendicular to the surface in this case has to be letter E. Weight is always the force that's straight down. Weight is always straight down. Well, the only force that's straight down here is choice C. So vector C is corresponding to weight. Then we want to know, well, which one's the friction force? Well, for that we need to understand the direction of the motion is down the incline. So if the object is moving down, the friction force needs to be the one that opposes that. So that's going to be choice A. I do want to point out vectors D and B. Although they probably look like that vector that I drew before, they really shouldn't be included on a free body diagram. The reason being is vectors B and D aren't new forces. They're just components of vector C. If you want to include them on a free body diagram, I highly encourage you to use maybe a dashed line and not a solid arrow. That way you don't think it's a new vector. So really, these vectors don't exist, and they should not be on a free body diagram. Let's go ahead and break this down into some numbers here. In this diagram, we have a 30 Newton block sliding down a 30-degree incline at constant speed. We want to know the force of friction, and we want to know the normal force acting on this. It might appear that we don't have enough information, but it turns out we do. I'm going to walk you through it. One of the key things to pay attention to first, though, is recognizing that it's at constant speed. It's very, very important to recognize that when it's at constant speed, it allows us to understand how the net force in the situation will create or equal. So since it's a constant speed, I know it's in equilibrium, which means I know the net force in my y dimension has to be 0, and the net force in the x dimension also has to be 0. My first job to be able to solve this problem, though, is to create my free body diagram. Once again, I'm going to draw all the forces that I know are acting on this object. I know that there's weight down, mg. I know that there's a normal force perpendicular to the plane, Fn. And I know there must be friction, or else there will be nothing there to oppose gravity. And since it's in constant speed, there has to be a friction force. It's also sort of a giveaway since I'm solving for the friction force, that there probably is a friction force. I am going to go ahead and I'm going to draw in my components of weight and my angle theta here. So this is my 30-degree angle, theta. And these are my components of weight. Now, like I said before, I'm going to dash these in so it doesn't appear that they're new forces. Rather, they're another way of looking at the existing weight. Remember, this is my angle theta here. This is mgy. And here is mgx. Now let's go ahead and write down our final few knowns. Since they gave me the object as a force, I know it's my weight, 30 newtons. So I know mg is equal to 30 newtons. And I also know theta is equal to 30 degrees. That's all I know. I'm looking for my friction force, and I'm looking for my normal force. Let's go ahead and look at the y dimension first. Because I know the y dimension, the net force has to be 0, I know that I have to identify all the forces in the y dimension. Now remember, the y dimension is the one that's perpendicular to my plane. Here I see a normal force, and I see the y component of gravity. Those are the only two forces in the y dimension. Because the normal force is pointed upward in the y dimension, I'm going to treat it as positive. So Fn is my positive force, and then I'm going to subtract my negative force, which is mgy. From that I see, if I add mgy over to the 0, I see that Fn is equal to mgy. Now because I know mg, and I know theta, I can set up mgy in terms of mg, just as I did in the prior slides. I remember that mg is adjacent to my angle theta, so I need to use cosine. So I know my normal force is mg cosine theta. Because I know mg and cosine, I can solve for this problem. 30 cosine 30. Go ahead and get my calculator and solve for this. Okay, I'm getting a value of 26 newtons. Do not make that 6, I'm sorry. And so therefore the normal force, part of what I'm looking for, is equal to 26 newtons. Done. Let's go ahead and find the friction force. Because the friction force is in the x dimension, it's parallel to the plane, I'm going to go ahead and look at my sigma fx to solve for it. Again, I know it's in equilibrium because I'm going at constant speed. So I look at my parallel dimensions here, and I see that I have a friction force, and I also have my x component of weight. Since the x component of weight is parallel to the plane and is in the direction of motion, I'm going to treat that as positive. mgx. Friction force is opposing motion, so I'm going to treat that as negative. Negative ff. Once again, if I rearrange for ff, I see the force of friction is equal to my parallel component of weight. Again, remembering that mgx, being opposite of my angle theta, is mg sine theta, I can plug in that mg sine theta. I can go ahead and plug in my numbers. 30 times the sine of 30, and I find out that this is equal to 15 newtons. And there you have it. The frictional force in this example is 15 newtons, and the normal force is 26 newtons. Let's go ahead and do another one. This one's a little bit harder, and by far the most difficult it gets for inclined plane problems. So it's really important that you pay attention to how this works. It's only a little bit more difficult than the last one. We have a 4 kilogram block sliding down a 27-degree incline at constant velocity. We first need to complete the free body diagram, but then once we do that, we also need to figure out all of the forces acting on it. Once we figure that out, we also need to figure out the coefficient of kinetic friction, or mu. So let's go ahead and complete that free body diagram. I've got my weight down, mg. Got my normal force perpendicular. And I've got my force of friction opposing the direction of motion parallel to the plane. Go ahead and break down my components of weight. Once again, using a dash vector. So I have mgy, I have mgx. I also have my angle theta right in here, right here. Well, I need to find all of the forces. I think the easiest one to start off with is finding mg. Remember, writing it in terms of a force, that's F sub g. So F sub g is equal to mg, which is equal to 4 kilograms times 9.81 meters per second squared. Go ahead and do the calculator work. Make a little bit more room here too. And we have an overall weight. We have an overall weight of 39.24 newtons. Remember, that's not only is that Fg, but that's also mg. Okay. Oops. Finding the force of friction and the normal force would be a little bit more advanced. This could be the same technique we used last time. Let's go ahead and find the normal force first. And for that, I'm going to look in the y dimension. And I see that the net force in the y dimension must be 0. It's in equilibrium. Which means to equal the force that's up the y dimension, Fn, minus the only force in this example that's down the y dimension, and that's mgy. Once again, the normal force is equal to mgy, not mg. However, mgy is still equal to mg times the cosine theta. Remember, mg is what we just found, 39.24 times the cosine of 27 degrees. And it looks like we have a value of 34.96. I'm going to go ahead and round that up to 35 newtons. That's my normal force. We're going to find the friction force in a very similar manner, but we're going to look in the x dimension, because the x dimension is the one that the friction force is in. And we know that the net force in the x dimension is 0, because once again, it's traveling at constant velocity. It's again very important to pay attention to. Constant velocity means net force is 0. Which means we're looking at mgx minus your force of friction. The force of friction is therefore equal to mgx, which remember is equal to mg sine theta, which is equal to 39.24 times the sine of 27. .81 newtons. Like I said, this is just like the last problem with one little additional step. We need to find the coefficient of kinetic friction. Remember, that's mu. There's only one equation where we can use mu, and that's an equation. The force of friction is equal to mu Fn. Well, now we have the force of friction, and we have Fn. So all we have to do to find mu is rearrange this equation. Mu is Ff divided by Fn, and then sub in for each value. 17.81 divided by 35. And it looks like we have a mu value in this example of 0.51. Now remember, mu has no units, it's just a coefficient, so it's just a just a number. And there you have it. That is the most difficult inclined plane problem. Now, of course, in class, we're going to go over more, this more in depth. We're going to have more practice. But if you just remember those basic steps in the beginning, which force is which, your normal force is in the y, your frictional force is in the x, and your weight is the one that's straight down, which is in both the x and the y. You break your weight up into your y and x components, and you set up your dynamics. Sigma f equals 0, sigma fy equals 0, and plug in and solve. Thank you, that's it. We'll go over this more tomorrow.